So what I'm going to talk about is my work, which started off about 7 years ago, where I was at the time working with Robin Milner on trying to raise awareness of ubiquitous computing. And then about 5 years ago, I got an ERC advanced grant, which I built around PRISM. And what I'm going to tell you is some outcomes from that work and also more generally work of my group, which involve PRISM, but also extend PRISM and necessarily have to go beyond PRISM. So this is based on a lecture which I gave in 2012, and it is a lecture series that Robin Milner set up in Edinburgh that recognizes theoretical work that has made some practical impact. So first of all, I wanted you to think about a typical city scene. I mean, that could be Beijing, you know, could be Stockholm, it could be somewhere in California, but try to think, where are the computers? Of course, if you are my age, you would probably remember that's what computers looked like. They were all mainframes. Floppy disks, that may be your generation, you probably remember that, but we were working with punched cards and even punched tape. So this was back in the 80s. But now, of course, we know that smartphones and tablets are taking over the world. I mean, smartphones are the most successful disruptive technology since the advent of the television. We use them for everything, you know, access, banking, etc., shopping, directions. I couldn't have got here without my iPad. Of course, we are developing homes that are smart. You may have heard the recent news of what Google spent about $3 billion on. Nest, this is a company that develops smart homes energy management schemes which learn from the user patterns, the usage patterns. But of course, we want these to do everything for us. Built around the network. Now this is a video that I showed in 2012, and this is a self-parking car, I mean a dream for me, and this is a mid-range car, a Ford Focus. Of course now I'm at Oxford, I'm working with Paul Newman, who's developed self-driving cars. And you know, these cars will very soon be on the road. I mean, most car manufacturers are now marketing these self-driving cars, which would at least, you know, partially take over from the driver. And of course, another recent news, iWatch. We don't quite know what it will do, but it is becoming a fashion item now. Okay, you know, it's smartphones and these devices that they monitor everything. They monitor your sleep, your heart rate. There are lots and lots of fitness apps. And if you go further, this is an implantable device. There is a miniature glucose sensor which is implanted under the skin. It's not on the market yet. It's planned to go on the market in 2017 and sends signals wirelessly to the watch to alert the user, you know, in case the glucose level is too low. So I've showed you some typical scenarios, but of course what all this is ubiquitous computing. Ubiquitous computing means computing without computers. So computing without computers as we know them, where, you know, you send them commands over the keyboard. Computers, instead, computing is everywhere in household devices. And they form populations. They are sensor-enabled because they can talk to the environment directly. They talk to all the devices. They talk to humans. They are embedded in the environment, and of course, they are also embedded in our body. They are controlled by software and autonomous. You don't have to send them commands. They make decisions themselves, and their role is really to assist you in everyday tasks. They are mobile, they have limited resources, and of course they form communities. And this is a 16-bit microprocessor. So this is the scale from the mainframe down to that size. This is a matchstick. Now, of course, this progress is unstoppable, and in future we will see more and more of these devices. Now, there are many perspectives on ubiquitous computing. It is not a new term. It is something that was introduced by Mark Weiser in '93 when he saw the trends of sales of mainframes and PCs, and he saw that this is what was going to happen. He called it the calm technology. Okay, where computing has disappeared into the background in such a way that you don't notice it. I mean, most people don't know that there is a computer, a very powerful computer, even in your smartphone. There are also perspectives on usability, and in particular, Adam Greenfield has introduced this term, everywhere, and that's not a typo. Everywhere means a device, an ordinary household device which does computing. And of course, there was Robbie Milner, who was a great proponent of the science of ubiquitous computing. And he was saying that we really need to understand it because it can then empower us. Now, what I'm going to talk about is a transition from theoretical results, but into practical software tools that have been applied in many of these scenarios and will be applied to even more of these scenarios in future. Now, the big question is, if you think about all those scenarios, in particular the last one, and self-driving cars, are we safe? Now, in the end, what you have is a computer program sitting inside that device. And you will have seen that, I think, on your PCs, but this is not something that you want to see if you are driving, if your car is driving, or if your insulin monitor fails to trigger an alarm. Now, if you think that this is an isolated worry or concern, there are many, many news stories, and I can give you an example of Toyota, which were fined about $2 billion for poor safety culture, but they are not, again, an isolated car manufacturer. The same happened to other car manufacturers, and this is all due to software problems. Not all problems, of course, are caused by software, but there have been software problems. And there is this wonderful title, Killed by Code. This is because there have been cardiac pacemaker devices which actually caused patient death because of software problems. So what do we do about it? I mean, as a computer scientist, I focus on the embedded software that's inside those devices. Engineers, of course, we know engineers, they have very strong, powerful methodologies to develop the hardware. We want to focus on the software, and that's the software on which your life depends. I mean, certainly in a self-driving car, your life depends on that software. So what we want is we want to have software quality assurance methodologies. And what I choose to work with model-based techniques and with rigorous software engineering. Rigorous software engineering includes formal verification as part of the software development process. And with that, you can consider properties such as safety, that the heart rate never drops below 30 beats per minute. Energy, you can analyze energy usage in certain safety-critical situations, etc. And what I work with is automated verification, where instead of guiding the theorem prover to develop your proofs, you develop a piece of software which actually does the proofs automatically for you. And I also focus on quantitative and probabilistic verification. And this is what quantitative probabilistic verification looks like. You have a probabilistic model checker. PRISM is an example of a probabilistic model checker. And what you need to provide as input is a model. And that model can be derived, from a protocol on your phone. We've done studies, for example, of Bluetooth and various other protocols and or some other parts. You also need to give it a specification. And that specification is then given as a temporal logic formula, but it's a temporal logic formula which includes probabilistic statements. So what it is saying, of course, maybe you don't want the phone to fail. So you'd be stating, my phone never fails. But in a probabilistic world, and all these protocols work probabilistically, they use randomization, you cannot prove that it never fails. You can only show that it fails. If it fails, the probability of failing is very small. And this is what that property is saying. Eventually, by time t fail happens with probability that is less than 0.01. But perhaps you might be interested in 0.00001. What you get out of it is, yes, this is true for my model, which you can then extract, perhaps maybe you've extracted it from software. You can get a counterexample, but you can also get quantitative results, which plot the probability or maybe some other quantities against parameters in the model and in the property. But of course, why quantitative verification? There is a lot of verification that is not quantitative, and it focuses, for example, on code in C, C++, or Java. But that is ignoring the very important aspects, and they are particularly relevant in the world of ubiquitous computing. Real-time aspects, they are all quantitative. Resources, energy, buffer sizes, etc., they are all quantitative. Randomization, all wireless communication depends on randomization, randomized protocols. And of course, uncertainty. We know that messages can get lost, but of course you want to be able to quantify the probability of a message getting lost, because that actually will then filter into the reliability of the software that relies on them. Now, the analysis is then quantitative, and it is exhaustive in the sense that model checking provides an exhaustive analysis, and it is as strong as a mathematical proof in cases where the model, the abstraction, is finite. Because in the end, we are running an algorithm, and the algorithm has to enumerate over a certain number of cases. And that's what quantitative verification does. And here are examples of quantitative properties. With a mathematical proof, you can show something that you are not able to show with simulation, or at least not easily. You can identify the worst case over a very large number of initial states. For example, what's the worst case probability of an outage? So I'm asking what's the maximum probability over for any possible schedulings of system components. I can also ask for the maximum probability of an airbag failing to deploy from any possible crash scenarios. Okay? And if you have something rigorous and automatic, this is the type of analysis that you can provide. And you don't only do it for probability, you can also analyze expectations for times and resources. But of course, that's verification, quantitative verification, as was then 5 years ago when I started on this project. And what verification does is it waits for a model that you provide, or maybe you extract from the software, and a property. And then the output is yes, or perhaps a counterexample, which they then have to feed back to the model to improve the model and eventually the system. But how about we actually try to take the property and synthesize, the model, the system, which is then correct by construction, because it guarantees that the property is satisfied. And the verification community is moving in that direction, and this is what we are working on as well, but we are looking at simpler problems, parameter synthesis, controller synthesis, and template-based synthesis before we can move into actual model synthesis, synthesizing structures rather than just parameters for a particular template. And there are many application domains and also connections to other areas, in particular robotics, which is now doing controller synthesis from temporal logics. In security, it can be used to generate attacks, strategy synthesis, and for dynamic power management synthesis. Now, historically, quantitative verification is not that new. The theory of quantitative and probabilistic verification is not that new, and in particular it goes back to Hansson and Johnson, who were in Sweden. In 1994, they implemented the first tool for a well-known probabilistic temporal logic, PCTL, and this is one of the logics that PRISM supports. But really, it wasn't until PRISM and also another tool, ETMCC, were introduced in 2000. And from that point on, these tools became established in many, many domains. And I mentioned some of them. Mads has already mentioned a few in the introduction. And we did find genuine flaws in real-world systems, and we also showed that you can correct them. And PRISM itself, when it started, we released it in 2001, so I was thinking about it yesterday. It's a teenager, 13 years old. It's barely a teenager, and it is still developing. It now supports, then supported 4, but now supports 5 different probabilistic models, and for each there is a corresponding logic, and it works on all major operating systems, and there are about 90 or even more than 90 case studies from all these domains, application domains that I've mentioned. But of course, I wouldn't be giving you this talk if ubiquitous computing were not presenting major challenges for PRISM. And in fact, the challenges are so great that we had to move beyond PRISM to actually make progress with some of the scenarios that I'm going to show you now. So I have selected 3 examples. One is that in ubiquitous computing, we need to model communities. We need to model communities, we need to model interactions between agents, both human and digital agents. And this is something that PRISM was not covering at the time. We also need to monitor and control physical processes. Just think about the heart rate or the insulin monitor. That's another example. And finally, we need to interface to biological systems. So you want to be able to identify perhaps a particular molecule and maybe target if it is a cancerous molecule. So these are the examples that I will just show you at a high level. Now, for each of these, we always started with theory, and theory had to be developed into practical tools, new verification algorithms, but these tools, some we added to PRISM, but most had to be actually done outside PRISM because the challenges are really insurmountable. So I'll show you those 3 examples. And first of all, modeling cooperation. We really need to consider ubiquitous computing as having populations of agents, but these are not slaves in a sense that your PC is a slave, just wait for your command. These are self-interested agents, and they have their own goal. Perhaps the goal is that, your fridge, and you've asked your fridge to buy you milk and also negotiate the best price of the milk. These are the kinds of scenarios that we are discussing. Now, this is something that is, of course, considered in economics, where game theoretic models are being used, and the key property used there is an incentive. Okay, if you want to model a population and also coordinate, that's what ubiquitous computing needs to coordinate. For example, in user-centric networks, in energy management, you need to incentivize agents' behaviors, so that the benefit is evenly spread across the whole. So the question was, at the time, can we actually automatically verify not only game theoretic models, but stochastic game theoretic models? And can we also synthesize winning strategies? So for a particular coalition or for a particular agent, can that agent win against any possible environment? And what we did is we looked at a concrete case study. So this is an smart grid energy management system which actually exists in Kent. It's a village in Kent. And these people, Hildman and Safra, they proposed a protocol, and it is a probabilistic protocol because the protocol for energy management, job submission is probabilistic because you want to have it decentralized, so randomization is used. They also measured the demand curve, so this is time of day. We discretized the demand curve in order to make it realistic. And we modeled it as a stochastic multiplayer game where you have every household is an agent, but you can then individually consider coalitions or maybe even individual agents, and you can consider their behavior against all the other agents. And what we did is we found a problem with the protocol. And the problem was that they assumed that all households are going to behave properly. They just, they incentivized, but they didn't de-incentivize. And in fact, what we had to do is we had to introduce punishment. So what you can see here is that if all follow the algorithm, so this is the average number of jobs per household. This improves over when you are not running the algorithm. But these here show that individuals, these are small coalitions, individuals can actually cheat, and of course they cheat at the cost of the grid. But if you introduce punishment into the system, this is the behavior, okay? So then there is no incentive to cheat. So this is one example that we have learned. But of course, this is a very typical example of what is needed in ubiquitous computing. Another example that we considered is inspired by the DARPA challenge. We developed strategy synthesis, but a multi-objective strategy synthesis, which we applied to maps of villages around Oxford. Now, what's the difference here? We have introduced a game theoretic model. So the environment itself is active, okay? The car, of course, the car makes decisions, and it also has to be probabilistic because of uncertainty of observations. But what I'm allowing you to do here is to consider an environment that is active, because that environment, of course, can have some other cars in the next lane. Perhaps the environment wants to make a decision whether to, the child should run onto the road, okay, etc. And I'm hoping to work now with the engineering science department at Oxford to take this work further and also develop probabilistic driver models, which are based on this. So this was one example, and for that we have developed an extension of PRISM, which is called PRISM-games, and you just supply it with stochastic game models. And there is a temporal logic, which is now based on ATL, alternating temporal logic. And in that logic, you can state properties about coalitions. So these are sets of agents, and you can state that, for example, they have a strategy to win something with high probability, or perhaps to obtain the smallest energy, but this is regardless of strategies of other players. So irrespective of how the rest of the environment behaves. And another example that I'm going to show you is physical processes, and this is also known as cyber-physical systems. Now we know that UbiComp systems have to control physical processes. I've given you several examples of that. I mean, even automotive control, just, think of airbag and, parking, etc. But what I'm going to show you is actually an application based around implantable cardiac pacemakers. So the idea is that we want to develop technology that can be applied more generally to implantable devices, but to start with, we wanted to learn, and we are learning from a reasonably well-established technology, because cardiac pacemakers are well established as they are now, but there are new devices coming in, and in particular, completely implantable into the atrium wireless devices and wireless pacemakers. They were implanted for the first time in the UK this year. And the idea was there that, again, we asked the question, can we apply quantitative verification? And at the time I was hoping, can we apply PRISM in order to verify the behavior of pacemakers and also synthesize timing parameters? That's how the work evolved. Now, first of all, I need to show you a little bit about the heart. So the heart spontaneously generates electrical signal, and this electrical signal is known as action potential. And you know it as the ECG pattern. And what it does is the signal is initiated from this node here, and then it's transferred along the network of cardiac cells, and it stimulates the atrium and the ventricles. And everything is fine if it works, but some people have diseases which are called arrhythmias, and one in particular which is called bradycardia, and this is where the heartbeats are actually missed, okay, or are slow. And this is something that is then corrected by implantable pacemakers. So the pacemakers, as they are currently done, they are actually implanted under the skin, but the leads are implanted directly into the heart tissue, and they sense the atrium and the ventricle, and their role is essentially to sense the impulses, and if the gap between the impulses is too long, it stimulates the heart so that you maintain the heart rhythm of 60 to 100 beats per minute. So it is a real-time system. And in fact, some people at UPenn have spotted it, and they have used UPAL. The timed automata model check also has relevant connections to Sweden. And Wang Yi worked on UPAL. So this is how we got interested in this model. But then if you think about it, if you want to verify the behavior of the pacemaker, what does it mean? Because it is an open system. It's an open system, so if you want to verify the pacemaker, you will also want to be able to provide the heart rhythm of a particular patient. So you need to close the loop. So what we had to work on is models of the heart, which you could then compose with models of the pacemaker. And the idea is that these models can then be adapted to the rhythm of a particular patient, and you can also show the different types of diseases and different types of behaviors. So the pacemaker itself is a timed automaton, and this is the UPAL model. And we have developed a number of models. One was based on synthetic ECGs, and another one which is actually a network of cardiac cells, which is a communicating network of hybrid automata, input-output hybrid automata. But of course, this is where we hit the problem, because we have timed automata, we have hybrid automata, and we are talking about something like 20 to 30 cells in a hybrid automaton. And we have nonlinearity, because we have continuous flows which are nonlinear. And how do we verify that? They also can contain stochasticity, because in fact, for a particular patient, the heart rhythm switches between diseased and non-diseased in a probabilistic fashion. So we also had to add stochasticity. So we have the full, stochastic hybrid systems, and these are just not amenable to verification. And in fact, what we had to do is we had to rely on simulation, and I'm working now with Cheyenne Mitra from Illinois, who has developed a tool that can handle these nonlinear hybrid automata. And we are relying on simulation, but it's a simulation which is heavily reliant on annotations that allow you to bound the dynamics of the system in a way that's sort of familiar to many, probably Lyapunov functions. These are, adaptations of Lyapunov functions, but with which you can obtain simulations that cover behaviors around a single simulation point. So you can run a single simulation, but you obtain guarantees on the behavior around that single simulation point for the dynamics up to some time. We have also developed approximate verification methods, which just essentially compute the proportion of the paths that satisfies the given properties. And this is what the results look like. So I'm showing you a heart which has bradycardia. So it's too slow because it beats only every 2 seconds. But if you compose it with a pacemaker, the pacemaker will then insert the correcting heartbeats. You can also do an energy consumption analysis. We have also a battery model which we connected to it. And I suppose this is the reason that this is important is because a pacemaker is implanted for something like 6 to 10 years, and then it has to be re-implanted again when it runs out of energy. This is why we are also looking at parameter synthesis, because what we want to do is we want to find the timing delays so that the energy is minimized in a way that is patient-specific but not disease-specific, as it is done at the moment when the surgeon is implanting the pacemaker. And with the simulation tool, we were also able to show that certain diseased heart models can have this alternating behavior, which is known as a precursor for some of the arrhythmias. So here I'm showing you, the power of the heart model that we are working with. But okay, for the tool support, we had to leave PRISM, and in fact we are working now with Simulink, because Simulink allows you to model timed automata, hybrid automata, also allows you to do stochasticity as well. And we have a framework. If you are interested, then there is a web page that I can show you that gives you a lot more information about that. Okay, and the final thing that I wanted to finish off with, okay, so we started off with population, okay, these many devices. We are moving into implantable devices, maybe even micro in the longer term, but that's not all. I think this is also taking us into the world of nano, because ideally you may want to do some of the detection, the disease detection and diagnosis directly at the molecular level. And that's because these ubicom devices will also need to interact with the real biological world. And there are many of typical scenarios And the specific application that we are working on here is we are looking at DNA computation. That is, take DNA molecules and design programs, DNA programs, that will achieve a particular outcome. And the question again that we had was, can we apply quantitative verification, in particular PRISM, because PRISM was already used at the molecular level. You can model chemical reaction networks directly in PRISM, so this was a relatively straightforward transfer of the technology, with one exception, with scalability. But of course, this is what computing looks like now, and the idea goes back to von Neumann, and it's very, very old. We think about bits, and we organize computation through logic gates. And we also know that hardware verification is now indispensable. I think ever since the Intel bug, it has become established in the hardware design, silicon design. Now, DNA computation is a very different paradigm. It is more like chemistry. And in fact, the economists have called it computing with soup. Why? Well, instead of laying out the circuits in silicon, in order to design a DNA program, you need to come up with DNA molecules. So these would be particular sequences of the base pairs, ACGT, okay? And for example, in this case, they designed at Caltech, they designed 130 strands, and you put them in a test tube. Of course, you put several millions of each of these 130 strands in a test tube, and that's all. You've done your design, and then from that point on is autonomous. Because molecules then engage in chemical reactions, they can bind, they can unbind, and at the end you can check whether they've done the result by fluorescence. Now this technology is slow, but I'll show you at the end what I'm working with physicists now, which is a faster technology. And by the way, that's not my quote. This is how the blogs reacted to this program. The program, it's a DNA program which can compute the square root of a 4-bit number. Okay, but it's a start. Still, it's a start. Now, DNA can also be folded into structures. Okay, so again, you come up, with these strands, and as before, you just have inputs, and then you watch out for outputs. Here, what you do is you take one very long circular strand and short single strands that would then pin that long circular strand into shapes. And okay, I'm working on a tile design with my collaborators, but they have designed these. I've seen a China map as well being designed in DNA. That was at Shanghai. Of course, longer term, this is what we want to be doing. And people have already developed these boxes, so you can take DNA, it folds into boxes with lids, and the lids, you can control the opening of the lids, so you can release, for example, some drug at a particular point in time. It's not immediate, but this is the general direction. And this is how a DNA gate works, okay? So what you have here is you have these double strands. Double strands is the hybridized DNA, and you give it this as input, this strand as input, and it's a transducer, so it converts X into Y. Y is the output. And so in order to design it, you have to come up with a design. So these X's and T's, they are specific sequences of base pairs, and they are all on these single strands. And you put all that into a test tube, but of course, in millions, for each of these in millions, and that's all you do. because then the reactions, are spontaneous. Now, what you can do with this is you can also link transducers into cascades. So you can transform X into Y and then Y into Z, okay, etc. And again, so seems very simple. And in fact, we were working on this. We were pointed in the direction of this problem by Luca Cardelli. And this is because that gate that I showed you is one that he designed. And then he realized that when he was combining it into cascades, is that there was a problem with it, and he couldn't immediately find the problem. They tried to find the problem with a simulation, but with this kind of number of molecules, millions and millions, it's impossible to find because it's a very, very rare event. So he said, why don't you try it with PRISM? And in fact, that's what we did. And so the flaw that Luca Cardelli found himself manually, we can actually now find automatically. And it's because of the fact that if you get the design slightly wrong, what you can have is that one gate can interfere with the process of another gate. And this is something that was not anticipated, and you have to put in stronger rules in the generation of the actual strands in order to make sure that this doesn't happen. And for this, what you can also do is you can analyze the probability of incorrect behavior. So what happens in that case is that if you put together two transducers, then they'll terminate, okay? And termination is a good thing, but there are two kinds of terminations. One is the bad termination, and the other one, the erroneous termination, and the other one is the successful termination. And they are both happening with probability about 1/2, and the probability of terminating is 1. So in order to correct it, you actually have to change the design, but then you can show that you do not actually get this erroneous termination. Now, another case study that I will not say much is this. So I'm now working with physicists, Andrew Turberfield, and what they are doing is they take the tiles formed from DNA, and the idea is that on those tiles, you can then print tracks. So these are Boolean decision trees, but they are certain molecules which are attached to the DNA origami tile. And you can now have a molecule here which will attach, and they know how to make it work. So it will detach and actually burn this molecule there and attach to the next one. They know how to control moving to the left and right. So you can imagine a lot of biosensor technologies can be built like this. And in fact, they have already developed it for tuberculosis in the States by Andy Ellington's group, not using exactly the same technology, but using a DNA technology. But of course, this technology is also very unreliable because we are talking about, nanoscale circuits. And these molecular walkers, they do not just move always to the next one. Sometimes they jump over two. They can also jump backwards, okay? So in those cases, you can also have deadlock because it will burn, some what we call anchorages, then, it can get stuck where it will not be able to go any further. So what we have also done is, in this case, we have just used straight PRISM, and we have analyzed the safety and reliability of those devices. And we can then additionally synthesize the rates of those walkers to guarantee a particular level of reliability. So this is all, but we didn't do it with PRISM. We did it by connecting a tool developed at Microsoft for doing DNA program designs, connecting it to PRISM. And this is the end of my talk, and I personally feel that this is a very, very exciting time to be a computer scientist, and I mean, it's even more exciting to be in this kind of, working with engineers who design these devices and look at these, issues that can crop up in embedded software, but also, also in the software at the molecular level, and of course, there are many, many challenges, and the problems are far from solved. Ideally, we would like to be able to extend PRISM with some of those techniques, but I think we need a lot more work. And I wanted to finish by saying thank you to all my collaborators on this and those who have funded my research. Okay, thank you.